Hello and welcome to this video. In this video, we will be looking at an example of a projectile motion question. This question is adapted from Chris Meyer's notes from 2018, and in this question we got Sonder, who was a ski jumping champion and designer of a modern ski used for ski jumping. The modern ski acts like a wing, providing the jumper with an upward lift force. In grade 12, we will ignore all the effects of air, so we will assume that air resistance is negligible. The story goes that Sonder wowed a group of spectators by jumping over a very tall rock. Let's explore the physics of this daredevil event. We will suppose that he launched from a ramp with a speed of 18 meters per second at an angle of 28 degrees above the horizontal. The edge of the ramp was 1.5 meters above the ground level. The tallest point of the rock was located 13.8 meters horizontally from the edge of the ramp and was 5 meters above the ground. The ground in this area is quite level, and we're looking to see whether or not he's going to make it over the rock. So let's see this through the three main procedures. We're going to do the pictorial view or the system diagram first, and we'll move to the physics representation after, and afterwards we'll do the mathematical representation. Just going to highlight the numbers in here so we have an idea. We got the ramp with a speed of 18 meters per second, 28 degrees above the horizontal. And we got the edge of the ramp was 1.5 meters above the ground. The tallest point of the rock was 13 meters horizontally and 5 meters above the ground. So let's draw all of those information down. So we got our ramp. The ramp was 1.5 meters here, so I'll put that in, 1.5 meters. And the angle of the ramp was 28 degrees above the horizontal, so that's here. And we get the jump, so the jump is going to be starting in this direction. Velocity of this is 18 meters per second, so the magnitude here is 18. I'm just going to write V1. So that's the initial velocity. And the rock is going to be somewhere here. So I'll draw the rock. It's probably a rock, something like this. And this is quite level, so we'll have it like that. The height of this one is going to be 5 meters. And we are going to have the jump, so this person will either jump so that it goes like this, or it's going to go and come down like this. We don't actually know what's going to happen, so the final velocity could look something like this, or it could be looking as though it's going upward, so we don't know. I'm just going to put in V2 here. That's all I know so far. And I know one other piece of information here which I will label as well, and that's the horizontal distance from here to the top of the rock. I'm going to name that displacement from 1 to 2, and I'm not going to put the value in. I'm just going to put the vector and the direction there. I know that there's going to be acceleration in the x direction. It's going to be consistent because we're going to assume that there's no air resistance. That value is going to be 0. There's going to be acceleration in the y direction, and that's going to equal to 9.81. And I'm just going to have all my accelerations with squiggly just so I know those are the accelerations. And the other piece of information that I can find out is the distance between the beginning to the top, the vertical distance here, distance 1 to 2 in the y direction, and this is in the x direction. So I'll label those so that I have an idea. Usually when we do these questions, we want to label velocities at the first stage and the last stage. In this case, we have the accelerations between different stages, which we have x and y, and the displacement between the different positions. The times we don't know, so we don't know how much time it takes to go from 1 to 2, and x and y is independent here, so that's just going to be a question mark there. That's all I have from here. Let's draw some component triangles so that we have an idea about V1 and V2. Again, V2 is a little bit unknown here. V1 is going to be in this direction. It's going to definitely have a component in this direction, Vx, and a component in this direction, Vy. And this is angle theta 1, or you can just call it 28 because you have the value there. And for velocity 2, again, could be going it could be going in this direction and then just get over the rock before it starts coming down, or it could have a max height and then come down. We don't know exactly, but that's okay. We'll assume at the moment that velocity is going in this direction, and if anything changes, we'll figure it out in later part of the question. So this is velocity 2 in the x direction, this is velocity 2 in the y direction, and this is velocity 2. I am also going to put all the information in a table, x and y. In the x direction, we have v1x, we have the acceleration is 0. We're going to make that assumption in parts in the word representation. And we have the displacements from 1 to 2 in the x direction. And that one we do have the value for. That's going to be 13.8 meters. And actually, I forgot a sign convention here. I'm going to use positive y in that direction and x in that direction. I'm going to put it in a nice cloud. And for my unit, I'll write it down here. It's meters. And v1x, I might need a little bit more space here, so I'm just going to expand this. And v1x is going to equal to V1 itself has a magnitude of 18 meters, so that's my hypotenuse. In this case, for the x direction, it's adjacent, and for adjacent, using trig ratios, it's going to become cosine of 28 degrees, and my unit is meters per second, and that's it. And the time is going to be shared between both of them, so I'm going to put that here. In the y direction, I need v1y. For v1y, basically we have the magnitude is 18, and it's for v1y, I forgot to label the ones here. It's the opposite to the angle, and therefore it will be sine of 28 degrees meters per second. The displacement from 1 to 2 in the y direction. In this particular case, the displacement, we got 1.5 meters up here. We got 5 meters, so it's going to displace 5 minus 1.5. So 5 minus 1.5, or we can just write it as 3.5 meters. And the direction is upwards in terms of the displacement, and that's the positive direction, so positive, it's good. We don't know the y value here, and we do know the acceleration is 9.81, but we're only taking the magnitudes here when we're putting these values in, so I'm going to put negative 9.8 because I know the acceleration as shown above is actually acting downwards because it's the acceleration to the gravity, and I've taken up to be my positive sign convention. I also often like to highlight this. That's very, very key and important. And now I have all my information in a nice table here. Let's now look at a few physics representations. So I'm going to go here and put B physics representation. And we'll start off by representing this. Actually, I may need to do it this way. X and Y, and we're going to do a motion diagram. In the X direction, basically, we know that there's no acceleration, so it's going to be a constant movement. So I'm going to have the spacing of my dots constant. And in the Y direction, basically, it is going to start at a high velocity, and it's going to slow down to 0, and it's going to come back down. So connecting these two together right at the beginning, that's where my point is. And then I will have a point here, point here, a point here, a point here. And then it will continue down. So going forward, it will start coming back. And at some point it will reach the ground. And the rock here is definitely in a height above the initial point, so it's not going to end up here. This is kind of like a very long procedure. It's either going to, so stage 1 is at the very beginning, and stage 2 is either going to be here or it's going to be here. And let's assume that that's 5 meters above, so it's one of these two. So we'll have to kind of think about that as we're doing the question and figure out exactly which point it is. We are also going to draw a few motion graphs, and we are going to start off with the X, and we'll then do the Y direction motions. And this is all going to be position, velocity, acceleration, and this is going to be in the X direction and the Y direction. In the X direction, starting off, I'll use purple here. I usually start with velocity myself, so we have a velocity, initial velocity is going to be positive when it starts. Basically, it's moving in that direction initially. And since this line is consistent and the velocity isn't changing, that would mean the slope of the position time velocity graph shouldn't be changing. And we know the acceleration is 0. We've already set that at the beginning of the question, and this is a two-stage question. So the displacement is going to basically end somewhere here, and I'm drawing the full motion here, but I will label stage 1 here and stage 2 here, and I like to put a circle beside them. In the Y direction, we start, actually I'll start here. I'll do the velocity first. For velocity, we start with a positive velocity, and then we basically reach a 0 velocity somewhere in between, and then we kind of keep going down. And that said, we know the acceleration is negative because we would have to take the slope of this line, or slope of tangents here, and the slope of tangents are always negative, and they're also just the same value all along, so the acceleration will be this, and the value of this is 9.81. We know that it's negative 9.81. We've already set that up there too, but we don't have to write anything down. These are just to give us an idea about how things will look like. And finally, actually we said as before, there's two possible positions for 2, here or here, so I'm going to label this as 2 as well. And for this graph, basically right here my velocity is pretty high, meaning that I should have a pretty large slope in the beginning. Right in the middle, 0 slope because velocity is 0, and then I have a negative velocity at the very end, so I'm going to draw it like this. And I know that 5-meter distance will either happen here or here. So I'm going to put 2 here. I don't know exactly which one is the right one at the moment, but hopefully later on in the question I can figure that out. And now that I have this, my final thing that sometimes I get students to do is the velocity vector diagram. So I'm going to shift this a little bit to this direction. And I know that velocity 1 is going like this, so I'll write that down, velocity 1. And velocity 2 is either going like this, meaning that the change in velocity is going to look like this, straight down. Or it could be that velocity 1 isn't changing, velocity 2 could be downwards like this, meaning that the change in velocity from 1 to 2. It's one of these two. We'll have to explore. In both cases, you can see that the change in velocity is downwards. And since the change in velocity is downwards and acceleration is downwards, it totally makes sense. Now, for the word representation for this question, it's all of our assumptions. So I'll write my assumptions right here, actually. Assumptions. Basically, we know that we are assuming that there's negligible air resistance. And that's going to cause the acceleration in the x direction to be consistently 0 and the acceleration in the y direction to equal to 9.81. It's just the magnitude, not the actual value, but maybe I'll just write it like this so that it's a little bit more easy to see. And that's it. That's my main assumption in this question. And again, I'm not sure whether you can also describe the motion a little bit if you want to do that. Basically, the person is coming in at an angle of 28 degrees with a certain speed. They are going to slow down in the y direction, so they're going to their height is going to reduce as they're going down. And we don't know exactly what their max height is, so they're either going to pass the rock on their way up to here, or they're going to pass it when they're arcing downwards. So one of those stages we'll have to see in the question. Okay, so that's our word representation. Let's do the math representation, and I need my table again. So maybe I'll just do part D beside my table. It's a little bit easier. So part D is the math representation. Okay, now what informations do I have in the y direction and x direction? Let's see. Well, in the x direction I have this and I have this, so that means I can find the change in time right away, which is beautiful. And once I have that, I can actually use that set of data to find the displacement in the y direction and compare it with this value and see if it's going to be bigger or smaller. Let's try that out. I am going to put in velocity in the x direction is equal to the displacement in the x direction, in this case from 1 to 2, divided by the time. I'm going to be taking, as I said before, right to be positive. I'll write it down here. I'm rearranging for time, so I'm going to write time is equal to, and I'm going to take all the magnitudes in the next step, or maybe I'll write it in one other step here, d, or position over velocity. And when I put the magnitudes in, I'm going to get position here is 13.8 positive because it's to the right, and velocity is also to the right, and my value there is going to be 18 cosine of 28, and I will get 0.8683 3 dot dot dots seconds. I'm not asked for this one, so I don't have to write it in proper number of significant figures yet. But I'm going to keep the actual value and use that value in the rest of the question. Now I have found my t-value, so I can actually use that information, this one and this one, to get this and just to compare the two values. So let's try that out. We have the information that we have. We don't have the final velocity, so we are going to use displacement from 1 to 2 in the y direction. I'm going to take up to be positive here, is going to equal to velocity 1 in the y direction multiplied by time plus 1/2 of the acceleration in the y direction multiplied by the change in time squared. And the time here is 1 to 2. And I can just plug in my values there. Velocity 1 is 18 sine of 28. The time is 0.868 dot 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 plus 1/2. My acceleration is in the negative direction, so it's not. So I always compare my up here. I know acceleration is down; they're opposite, so I'm going to use a negative value here, negative 9.81, and the time is going to be the same. I'm running out of space here, so I'm just going to move a little bit in this direction. And the time is going to be 0.868. Again, I'm using the exact value from my calculator and not the rounded values. Alright, here I forgot the square sign, so I will put that, and then I will get 3.639 as my final answer. So rounding this to proper number of significant figures, we got my displacement, or all distance is fine, is going to equal to, actually approximately equal to, I believe the lowest number of significant figures in this question is 2, just going back and checking and making sure. I have 18.0, which has 3 significant figures, 28 has 2, 5.0 has 2, 1.5 has 2. My final answer then, because I've been multiplying and dividing all over the place, is going to be 2 significant figures, the lowest out of the rest, meaning that my displacement, or my distance, was 3.6, but I want to also give you the direction, which is in the upward direction, because I got a positive value. And since this is the case, I am not going to write the rest of the solution down. I'm just going to kind of make it small like this so you can see it. But we got 3.6. The distance of the rock is 3.5. So basically, in this case, it means that it does work, because based on theoretical value, the person can be at a height of 3.6. We can do a little bit more calculation to figure out whether it's this position or this position exactly, but it's not a huge importance at this point. All the fact that we have this value tells us that he will be above the rock at this time. The other thing to take into consideration, though, if you're evaluating this question, is the fact that there is going to be air resistance. And air resistance can actually help him in certain situations, because if the surface area of the ski is large enough, the air particles will actually hit it and cause them to come down a little bit later. So it will slow down the rate at which he's coming down, and that could be very helpful. And if it's angled like this, as air particles are hitting him, they're causing a upward force on the skier. So that could actually help the person stay airborne a little bit longer. It's very similar to as to when you're throwing a paper airplane. If there was no air resistance, your paper airplane would just fall. But since there is air resistance beneath the wings, it will cause the airplane to stay afloat a little bit longer. And that's what you can do with good designs. You can design skis that can actually take advantage of that and keep you in air a little bit longer. And that's kind of the stuff you need to think about when you're thinking about the evaluation part of the question. What happens if the assumptions that I made are actually not there? And what are the consequences of that? All right, folks, I hope this question was helpful in giving you a little bit idea about how you can work on projectile motion type of questions, and have a wonderful day.